All right, guys, so we're starting to graph all of these different polynomial functions, and we have a whole bunch of different degrees that we could start off with. So previously we've graphed parabolas, and they're all second degree, and so we can have this technique that we use for every single parabola. Well, polynomials, they're all going to look different because you've got different degrees that you could have. The leading coefficient could either be positive or negative, so you've got tons of different options. So our best method that we can use so far is just by plugging in some different values into a table and kind of seeing how the graph takes shape. So one thing that's super important, and this is what I just mentioned here, make a table and then connect them. Knowing the end behavior will assist you in completing the graph. So we're still going to write that down just like we did in the previous section. So we're going to look at this leading term, and this leading term is going to tell us everything we need to know. So if you look back at the previous section, what we just had here was an odd degree with a negative leading coefficient. So we know that this is supposed to be the end behavior right here. So I'm just going to copy that down onto our new problem. So this is our end behavior, just so we know what to expect. Okay, so two things. Because it's odd, we know that we're doing opposite things on the two ends of the graph, and then because our leading coefficient is negative, we know that these are opposite from each other. Like as we go to the right, we go down. As our graph goes left, it goes up. Okay, so that's what we know from the fact that this is a negative odd leading term. So we copy that from the previous section. Now we're going to make our table of values. We're going to start with kind of a standard -3 to +3 and then see if there's anything else that we should plug in. Okay, so start with this. -3 to +3 is going to be your standard, and then, like I said, we can kind of go from there if we need to show anything else. So those are the x values we're going to plug in. I'm going to show you guys a wonderful trick that I highly suggest you use. So what I want you to do is go to a calculator page, and it doesn't matter, you can either add a calculator page to your current document or just stay with your current calculator page. Okay, so we've got a calculator page. We're going to define our function, and then we can just plug it in super easily. So hit this menu key right here, and then you're going to just take that first menu, actions. You want that actions menu. So if you've got your calculator, do this with me right now so you can practice. And then define. So it's just menu 1, 1. It's super, super easy. And then we're going to type this in, exactly what's written here. So f of x, take f off of the alphabet pad down at the bottom, parentheses, x, close the parentheses, the equals is up here, and then just type this function in. So negative x to the third, and then minus 4x to the second, plus 5. So you just type your function in. When you hit enter, it'll just say done. And then for all of these, you can just type in f of -3, just like that notation that we've been using. So you type that in and then hit enter, and it'll give you the value. We don't have to, spend any time plugging these in by hand because that would be painful. F of -2, we get -3. F of -1, we get 2. F of 0, oops, I forgot my parentheses. Make sure it's in parentheses. It's 5. F of 1, 0. F of 2 is -19. F of 3 is -58. Okay, so you can see the end behavior happening. Here we say the bigger the x values get, as x values go off to the right, f goes off to -infinity. That's what's happening there. We're also supposed to go off to the left and see our graph shooting up to +infinity. We didn't see that, so let's plug in another value or two. Try 4 or 5 just to make sure we can see that end behavior happening. So plug in, -4 and -5. So f of -4 gives us 5, and f of -5 gives us 30. Okay, so there it is. So we can see our end behavior here. So we're not going to plot these huge points. We'll probably plot these ones and then probably that one. Okay, so we'll do a quick sketch. Okay, so we've got the point -3, -4. That is right there. We've got the point -2, -3, -1, 2, 0, 5, 1, 0, 2, negative 19, so that would be way down there, so we're not even going to plot that one. And then jump here, we've also got negative 4, 5, so that is up here. All right, so just do your best to kind of connect the dots here. So we know off to the left, it should be just shooting up like this. And then it does this. Comes up to this point, turns around, and then it's just going to go down towards negative infinity. So it's going to look something like this. And we're just going for a sketch. It doesn't have to be perfect. All right, so the next thing we're going to mention is something called the location principle. It helps us to find x-intercepts. And like I said, we did this with the previous chapter. We did it just with parabolas. But most of these, you couldn't solve them by hand even if you wanted to, and there's no quadratic formula or anything like that. So the location principle says this. If f of x changes sign, from one x value to the next, changes sign means like it goes from positive to negative or negative to positive. There's an x-intercept between those two x values. And now we've got 0. We could call them 0. We could call them x-intercepts. Okay, now I'll kind of explain based on this graph right here. So you can see like right here, my function changes sign. I have a negative y value, then a positive y value. So that means there must be a 0 somewhere between these two. And there is. If you look on the graph, here's negative 2, here's negative 1. It does cross through the x-axis somewhere in between. And then if we look for another sign change, there's another sign change right there. And this is actually, well, here's the positive one, here's the negative one. So we know it crosses somewhere between 0 and 2, and we know it crosses right here because we actually come up with 0. And then if we trace back to, let's see, this is hard to see, but between negative 3 and negative 4, so since I wrote them in different places, negative 3 I have a negative y value, and at negative 4 I have a positive y value. So you can see there's another x-intercept between those two. So that's what the location principle tells me. So I'm going to look at a table on my next equation here to see if I can find all the real zeros. Okay, so we are going to plug this in and make a table out of it. So menu and then 1, 1 to define, and we'll type this in. So f of x, you type it in exactly as it's written, equals x to the 4th minus x to the 3rd minus 4x squared plus 1. So again, you hit enter, it'll just say done. So let's do our standard negative 3 to 3. We'll see if we need to add on any more. Okay, we're just going to plug those in. So f, and then in parentheses you put whatever you want to plug in. Okay, so we got, 73. Okay, f of negative 2, 9. F of negative 1. So there's a sign change. We got our first sign change right there, so we know there's going to be a 0 somewhere in between those two values. F of 0, we got another sign change. So then it goes from negative 1 to 1, so there's another 0 right there as well. F of 1, and another sign change, that's another 0. So that is negative 3, so again we've got another sign change there. F of 2, got negative 7, no sign change, so it's still down below the x-axis. F of 3, 19, there's another sign change. Okay, so those are all of your sign changes. So that is where all of your zeros are going to occur. Okay, so between negative 2 and negative 1, so we had a sign change, and then between negative 1 and 0, again between 0 and 1, and then again between 2 and 3. So that's what the location principle tells us. So just quickly we can plot these points and get a sketch. Okay, so I'm not going to plot this point, it's way too big. I can plot this one though. Let's go by 2, 4, 6, 8, 10. So here's the point negative 2, 9. point -1, -1, 0, 1, 1, -3, 2, -7, so this is 2, 4, 6, 8, and then 3, 19, so that would be higher than that. Okay, so it's going to look something like this. It'll come down through this point, up, down, and back up. Okay, so it is an even power, so it should be doing the same thing on both ends, and it's a positive even power, so it should be going up on both ends. And you can see we have these 1, 2, 3, 4 zeros that I mentioned, and they fall exactly where we predicted they would based on the table. All right, in the second video, we're going to talk about minimum and maximum points. So I'm going to draw you just a little sketch to go off of. Let's say we have an odd function like that. We're going to define two new things. We've got a point that looks something like that. That point, it's like a little hill in the graph. We call this point a relative maximum value. So it's not a total maximum, like it's not the highest point ever, but it's the highest point in the general vicinity. So that's what that word relative means. Relative to the other points around it, it's higher. And then you have these little valleys like that, and so that is a relative minimum. So again, not the lowest point that the graph ever hits, but it's lower than the points around it. Relatively speaking, it is the lowest point in the general vicinity. So those peaks and valleys, we call them relative maxes and relative mins. Another word that we have for those is turning points. So we've got those right there. So maxes and mins are also known as turning points. So turning points basically means when the graph kind of flips and changes direction. So here it's headed up. There's a turning point. It flips and heads down. There's a turning point. It flips and heads up. All right, so this is super, super important. The graph of a polynomial has at most n-1 turning points. And we actually mentioned that in one of the previous videos when we were doing these general shapes. So I want to remind you of this. We talked about how this is of degree 1. 1 minus 1 is 0, and so it never changes here. This is degree 2, so 1 less is 1. It's got 1 turning point. This is degree 3, so it's got 2 turning points. Degree 4 has 3 turning points, and degree 5 has 4 turning points. So that's what this line means. All right, that has at most n-1 turning points. Super important. All right, so we're going to graph this function. We're going to do it with that menu define, like we did in the previous video. So we're going to set up, like I said, just our classic table here. If we need to add on any more values, we will. Okay, so we know that this is an positive odd function, so we should see it do something like this. All right, off to the left it should be going down to negative infinity, off to the right it should be going up to positive infinity, so we want to make sure we see that pattern happen on the table. Okay, so we are going to do that menu actions, one for actions and then one for define, and then just plug this function in. So f of x equals x to the third minus 3x squared plus 5. Okay, then we can just plug these values in. So f of -3 is -49. Okay, so we definitely see it going off towards that negative infinity. F of -2 is -15. F of -1 is 1. F of 0 is 5. F of 1 is 3. F of 2 is 1, and f of 3 is 5. Okay, so let's add one more just to show that it does keep growing after that point. There we go. So we see the 21, so you can see it's going off to positive infinity. All right, so let's give a quick sketch. Okay, so these values are really, really, really low. Let's scale by 2. -2, 4, 6, 8, 10, 12, 14. So we can sketch this. -2 be down at -15. -1 is at 1. 0, 5. 1, 3. 2, 1, 3, 5, and then 4, 21 would be way up here. All right, so we see it does something like this. Okay, so that's very similar to the shape we were expecting. Now here's the important part. Estimate the x-coordinates at which the relative maxima and minimum occur. Okay, so you can see there are these two turning points. Okay, so we think the max occurs, and we're not necessarily going to say it occurs at 0 because we didn't plug any of the decimals. Like, we're not sure that it happens there, but we know it happens near 0. Okay, so somewhere around there, and then the minimum is happening somewhere around 2. Okay, so that's what you guys do for that. You should identify max and mins, and you can see on this table, see how the values are going up, they're going up, they're going up, and then they go down. And so this was actually a change right here. And they're going down, and then they go back up. And so that was another change here. So at 0 and at 2, we had those turning points approximately somewhere near those x values. Okay, example 4, we're going to look at another graph that we can see based on this equation right here. So the weight of a patient during a 7-week illness. Okay, so we can't have negative values here. That wouldn't make sense because we got to go within the context of the problem. It says a 7-week illness, so we're going to plug in 1 through 7. Okay, so and then W. So let's go 0 through 7. Okay, so we're going to plug in this function. So menu, 1 for actions, 1 for define, and we can type in W of n, just type it exactly the way it's written, equals 0.1 n to the third minus 0.6 n to the second plus 110. Well, it doesn't like that. Okay, I must have W defined somewhere else, so you don't need to change this. I'm just going to change it and see if I can get a different variable. Let's just try Y. No. Anything? B? Yep. Okay, so you can see I have a ton of pages open, so W must have been used already. So normally you'd be typing W, but I'm going to type B of 0. It's 110. B of 1, 109.5. So this is the weight. So you can see they're losing weight at this point. 108.4. B of 3, 107.3, still losing weight. Let's see if we get a turning point anywhere. Nope, 106.8. 5. There we go. That was our turning point. So now they start gaining weight again. Oops, not W. B of 6, 110. Okay, back up to normal. And 114. Okay. So those are the values that we are looking at. So we've got these. We're going to graph the function. So we only need these positive values, 1 through 7. And then we're going to put a little split in the graph here so that we can start at like 106. 6, 7, 8, 9, 10. Okay, so our patient starts at 110, and then 1 week later, 109.5. 1 week later, 108.4. 107.3. 106.8. Back up a little bit to 107.5. Up a little bit more to 110. And then 114.9 would be way up here. All right, so it's going to look something like this. You just connect the dots. Okay, so something like that. All right, so that's the first part. That's the graph. We've got some questions. Describe the turning points of the graph and its end behavior. Okay, so turning point. Near, and what was that? That was week 4. Week 4 was when we started seeing a positive change, starting to gain weight back. And then the end behavior, we can say that the function approaches infinity as x approaches infinity. And we're not going to talk about negative infinity because negative infinity doesn't make any sense in this context. Okay, what trends in the patient's weight does the graph suggest? You can see that they're losing weight for a while and then started to gain weight back. Okay, so patient lost weight for 4 weeks. Then started gaining it back. Okay, and then will it continue indefinitely? No, probably not. We can probably assume that they might gain weight for a little while since they're getting healthy again, but it's not reasonable to assume that the patient's weight will rise indefinitely. Okay, so let's say it is unlikely the weight will rise indefinitely. Oops, unlikely. The weight will rise indefinitely. I suppose it's possible, but probably not.